All right, chapter 5. I don't think this is a very hard chapter to me. I think it's easier than chapter 4 was. So if you had issues with chapter 4, I think you might find chapter 5 to be maybe a little bit easier. We're going to be talking about normal distributions, and we're going to be talking about z-scores. So with the normal distribution, when we get that sample, what we're trying to do is estimate what the population is. And the larger our sample is, probably the better, depending on what you're doing. But generally speaking, the larger the sample, the better. So if you take your distribution, so these are the scores here, and you kind of superimpose a normal distribution over it. In theory, the more people that we add to our sample, the more it's going to round out and eventually will look like that normal distribution. So this one kind of already does look like it, but the more points that we get, data points we get, this will come up a bit, this will come down just a hair. Eventually it should all level out to be that normal distribution. So that normal distribution, the normal curve, theoretical curve, and it's known for its symmetrical bell shape like that. You can see it right here, this line here. Because this a normal distribution, let's say this is perfect, it's bell shaped, so if you divide it along the midpoint here, they're going to mirror each other. So if you folded them over, they would look exactly the same. When you look at this normal distribution curve, if you imagine cutting it here in the middle, if you folded it over, they're going to look exactly the same. It tapers off equally to the points at the other ends. On this on a normal curve, when you're dealing with like this hypothetical normal curve, your mean, median, and mode are all going to be right here. So in this example, 69 inches would be the mean, it would be the median, it would be the mode. And we talked a little bit about this last time, the idea that once we go out one standard deviation either way, we're getting about 68% of the data, so it would be somewhere in this area here. It would be about 68% of the data would be in this area. And then if we did 2 standard deviations out, so it would be somewhere in this area, somewhere in this area, we're getting about 95% of the data. So there would only be 5% of the data here at the very end and here at this very end. 5% total, so it would be 2.5 at one end and 2.5 at the other end. One of the reasons that we're talking about all this is so we can talk about the z-score. And it is a standardized score that tells you how far a score is, standard deviation wise, from the mean. So z-score, it's a standardized score, and it changes all the scores to essentially their measurements in standard deviations from the mean. And so you can get a data point and you can find out how far away it is from the mean in terms of standard deviations. And so again, we talked about this we've hinted at it. The idea that if something is 2 standard deviations away, it's probably an outlier. So there's a few different reasons to get that z-score, outliers being one of them. Another one is that you can compare 2 different scores on 2 different things together when you get those z-scores. So like if you get scores, sample scores for like the SAT, and then you get a sample scores from the ACT, you can't compare the SAT and the ACT together because they're completely different scoring systems. But if you change all of the scores to z-scores and you see that somebody has a 2 z-score, 2 standard deviations above the mean, you'd be like, okay, well, they're in their top. And so also you can compare 2 different people. So if one person has what seems like a really high SAT score and you're not that familiar with the ACT, and you compare their z-scores, if one person has a 1.1 SAT score, but they have a 2.5 ACT score, that's going to say that, this person with the ACT score is maybe, scoring better on these kinds of tests. Myself, I took the GRE many years ago, and they've changed the test since I took it. But with a z-score, I could compare my GRE score to someone that takes the GRE now. We could compare our 2 scores using those z-scores. Or I could compare my GRE scores to your SAT or ACT, whatever you took, if I wished. It's a pretty simple formula for this. So we're going to take whatever the score is minus the mean divided by the standard deviation. So whatever the score is that we're looking at, we're going to take that score, we're going to minus the mean from that, and then we're going to divide it by the standard deviation. This is an example. Let's say if you're looking at an IQ score, the person gets 135. And the mean on this IQ test is 100. The standard deviation is 15. You take 135 minus 100 divided by 15. So yeah, 135 minus 100 divided by 15, and that's going to give you a z-score of 2.33. Again, 2 standard deviations above the mean. That's pretty high. They're definitely in the top 2.5%. You know, we talked about percentile rankings before, so we know that her IQ score is going to be at least the 97.5 percentile. So we'll have on the homework and the quizzes, we'll have some where you can do these z-scores by hand, and hopefully that'll make a little bit more sense. But yeah, again, it's a pretty simple formula. The score minus the mean, both those divided by the standard deviation. So I was talking a little bit about percentiles, and I just knew that one off the top of my head, the 97.5, but most of them I don't know in my head. I don't have in my head. So there is a table that you can look at, and it's table A in appendix C. I'll also post it on Canvas so that you can look at it. But what you can do is take a z-score and then go to this table, and you can see where it ranks as far as percentile. And so in this example here, if you have a z-score of 1, which is 1 standard deviation away from the mean, this is divided in half. So we're going to be looking at either the 50 percentile and up or 50 percentile and down. So this score of 1 is at 34.13. So it's going to be somewhere in here. So 34.13. That's going to be plus the other 50% on that end. So 50 plus 34 gives you about an 84. So a score of 1 is going to be about, score of 1 is going to be in about the 84 percentile. It is 0.34 from the mean, which is that 0, or for in this case, 0.5. It is also about 0.1516 from the other end, and that's what this number is here. So yeah, about the 85 percentile. You can also, so this is kind of mirrored as well, so if it's, if let's say it's a -1, like where do they land at if they're -1? It would just be that end of the distribution, so it would be 0.34. So it would be somewhere in here. -1 would be somewhere in here. So someone that has a z-score -1, they're going to have a percentile ranking of about 34%, which means that you take that, which means you have about a 1.5 to get to that mean, which is this number here, again, the center line of it. So yeah, 1.5 plus the 0.5 for the other side, you're looking at about 65% of the people scored higher than this person on the test. Yeah, and so yeah, just again to reiterate, 1 standard deviation either way, that's going to get about 68% of the scores, and then 2 standard deviations away, it's going to get about 95% of the scores. And then there's an example here. So you'd go back to that table in appendix C and find the proportion of the total area identified with a z-score of 0.18. Now, just from what we've talked about, we know that a z-score of 2 is going to be about a 97.5, so that 1.8 is going to be somewhere in there, 95, 94, somewhere in there. So we'll go back to this table. I know this is hard to see. You can, again, get them on Canvas and you can scroll in. It looks like a 1.8 is about a 0.46, so it's going to be 0.46 plus the 0.5 from the other end. So you're going to have they're going to be in about the 96th percentile with a z-score of 1.8. At this point in the class, you probably want to have SPSS by now. If you haven't gotten SPSS, you should get it. I am going to do the z-scores in Excel and SPSS just for the people. Some people have problems getting the have trouble getting SPSS set up. So I'll show you how to get z-scores in Excel and SPSS. I'm just going to put a random distribution. Okay. So if you recall, you're going to have each score, and you're going to need to be able to have the mean and standard deviation. So you can figure those out pretty easy. Click equals. We're going to put AVE average. Double click the average. You want to get those numbers like that. Click enter. And so our mean or average for this sample is 4.09. To get the standard deviation, ST, and yeah, let's say it's a sample. And then we'll click this here. Again, that standard deviation would be different for population or a sample, but for the purposes of this, it doesn't matter. Okay, so each one of these scores, we're going to have to take minus the mean divided by the standard deviation. And this gets a little bit difficult. This is actually way easier in SPSS, if you ask me. You're going to click equals. You're going to click your x value, which the first one's a 2. I am going to put those in parentheses so that it will do that operation first. Click minus, and then we click the mean in parentheses divided by the standard deviation. So a 2 is going to be a z-score of negative 1.45-ish, which that seems about right if the mean's a 4. Just to show you how I did that again, I'm going to click equals. I'm going to start parentheses. I'm going to click our x value. I'm going to take the mean minus that in parentheses, and then it's divided by standard deviation. Enter. Now, we need the z-scores for all the scores though, and so you can't just actually take this and drag it down because it drags these down too when it's going back to do the formulas. And so what you got to do is make that formula static so that it doesn't move this part down. It's not too difficult. So I'll put a $sign in front of the D and a $sign in front of the 1, and then same thing over here, $sign here, $sign here, and that will keep those two numbers static. So when I drag this down, it will keep those two numbers like in the queue. So pull this down, ta-da! Now I have all the z-scores for this distribution. And if you look at it, so like so the 6 that's above the mean, it is a 1.32. That makes sense. And it is A6, which is that number there, minus D1 divided by D2. That's how you do it in Excel. Copy this. We'll open it up in SPSS. Okay, so here's our sample in SPSS. What we're going to do here is click Analyze Descriptive Statistics. Descriptives. We're going to move this one over. In theory, we can look at some different things here with the options and all this. But for the z-score, we don't need any of that. All we need to do is click this box right here. Save standardized values as variables. And so what it's going to do is it's going to save those z-scores right next to these the actual scores. It gives us the output. It shows us the minimum, the maximum, the mean, like we had in the Excel, the standard deviation, like we had in Excel, and then see, there we go. You'll notice that these numbers are the same essentially as the ones that are in Excel. Again, how I did that, I clicked Analyze, I clicked Descriptive Statistics. I go over here to Descriptives. Let's just reset it. You're going to take your variable and you're going to move it over to this variable, over to that side. Later on, we'll do some other things, like you could look at the variance, the range, how the distribution, what it looks like. But for this that we're doing today, all you need to do is click that to get the standardized values, the z-scores. There they are again. For the homework for this, so we'll do some of these z-scores by hand, but I don't think they're that hard. Preferably, you'd like to do some in SPSS, but if you don't have SPSS figured out yet, you can do Excel. You can follow those instructions that I did before the SPSS. All right, that's it for Chapter 5. Again, I don't think it's that difficult. I do think it's easier than Chapter 4. Thank you for listening.